Okay, so we're in the module on linear algebra, and we were talking about Gaussian elimination, LU factorization, which is easier to solve and which takes longer to code. And by most importantly, which takes longer to compute, how many operations. So we had gotten to the part where we were solving UX equals G. So this is by backward solving. And so we were here. And so I was just getting ready to say that the number of multiplication and divisions for this, for each X, is n minus 1 plus 1 times n minus 2 plus 1. And, oh, that's a plus. I apologize. This is a plus. All the way down to 1. And so this becomes the sum n I equals 0 to n minus 1 of n minus I. And we already know that we're using those formulas. So this just comes out to be n times n plus 1 over 2. Hi, Kayla. And the number of additions and subtractions just becomes n times n minus 1 over 2. I'm going to spare you some of these details because there are too many details right now for what we need to do and what we need to cover. Okay. All right. So the last, if we solve AX equals B, then the multiplications and divisions of LU, because we're doing LU is equal to, A is equal to LU. So for the first one, you have n cubed over 3 minus n over 3. And then for the second one, you have n squared over 2 minus n over 2. And then for the third one, you have n squared over 2 plus n over 2. So this just turns out to be n cubed over 3 plus n squared minus n over 3. And that's approximately n cubed over 3. Okay. And the additions and subtractions of LU to find X is n times n minus 1 times 2n minus 1 over 6. You should recognize that as the sum of I squared over 6 plus n times n minus 1 over 2 plus n times n minus 1 over 2. Okay. So if we do this, this also comes out to be approximately n cubed. And this comes out to be n cubed over 3. Okay, so what we find is the number of addition and subtractions is about the same. as the number of multiplications and divisions, which is approximately n cubed over 3. So clearly you can see that you have all these addition and subtractions and all these multiplications and divisions. The bigger the matrix is, the more operations it takes to solve. So these are the 3 major points. So the first point is going to be solving AX equals B is cheaper than multiplying 2 n by n matrices. Two n by n matrices. And that's basically n cubed operations. The second thing is approximately n squared operations are necessary to solve AX equals B. Once you know A is equal to LU. And then the last thing is it's much cheaper to you than Kramer's rule. Okay, which uses determinants. That has n plus 1 factorial operations. Okay, so if n is equal to 5, Gaussian elimination will be approximately 65 operations considering only multiplications and divisions. Why did I write that out? Whereas Kramer's rule, I don't know if you guys remember Kramer's rule. I love Kramer's rule. Is approximately 720 operations. Now, why do we care about that? Okay, well, let me explain to you one thing. As a researcher, so my graduate students' code would take 3 days to run. So we wanted to try to make sure we had as the most, what we call streamlined, efficient code so that we wouldn't have to deal with that. Okay, so let me give you the algorithm for this. Okay, so we want to reduce A, B to UG. Okay, so this is one augmented matrix to another. And then when we get to UG, we back solve. Okay, so we have 4K equal 1 up to n minus 1. Then we check to see if AK, so if AKK is actually equal to 0, then use an error message. And then you break. Because this does not allow for any one of our pivots to be 0. So if that's not the case, then you go on and you do for I equal K plus 1 all the way up to n. Oh, I forgot. I'm supposed to be writing like Fortran. So let's do, this goes to n minus 1. And this is K plus 1 up to n. Then you find m at ik, and that's going to equal a at ik divided by a at kk. And then once you find that, you'll do for j equal to k to n. I'm going to do aij is going to equal aij minus mik times akj. And then bi, I'm sorry, I feel like that should be, why is that bi? Let me check that. I need to check this. This is what's in my notes, but I'm feeling kind of not right here. Minus mik times bk. And the reason why I'm feeling kind of funky about that is because I don't feel like that needs to be in that loop. I feel like that should be out of the loop. I do. I don't feel like that should be in the loop. Okay, since I don't feel like that should be in the loop, I'm going to pull it out. I just don't feel like it should be in there, but I will double check. So then this would be b at I would equal b at I minus m at ik times b at k. Okay, and then I need an end for here. And I need an end for there. Okay, so then after you do that, you have to do back substitution. Hi, babe. Okay, and so then we would do 4 k equal to n minus 1 to 1. And I don't know if you know, you do it backwards. So that tells it to do it backwards. So then xk is equal to b at k. And then 4 j equal to k plus 1 to n. I get x at k is going to equal x at k minus akj times x at j. That whole thing divided by akk. And then that's the loop on j. So that should end. And then x at k should be nope, that's it. So this line right here, okay, that's why my notes look like that. So this line right here is xk is equal to 1 over akk times bk minus the sum j equal to k plus 1 up to n of u at kj times xj. Okay, so that's what that is. Okay. All right. So now this is all done without row interchanges. Now, the great thing about MATLAB, which is the matrix library, so MATLAB has changed my notes. Because in MATLAB, if I want to solve AX is equal to B for X, does anybody know what the command is in MATLAB?
I think you should put in the numbers in A.
Okay, you would put everything in A, so you would make sure you
Yeah,
have the matrix A
for
defined,
A and B.
right?
Yes.
And so then you just do X is equal to A inverse B.
Inverse of yeah.
And it just does it for you. This does Gaussian, and this does whatever numerical method, whatever it finds to be the most efficient numerical method to solve that. So, MATLAB has changed the notes, all right, because my notes, don't take into account that people are no longer really writing these codes. Okay, so let me say something about row interchanges. Number 5. Okay, so for row interchanges, let's say we have x1 plus x2 plus x3 is equal to 1, x1 plus x2 plus 2x3 is equal to 2, and x1 plus 2x2 plus 2x3 is equal to 1. Okay, so that gives us 1, 1, 1, 1, 1, 2, 1, 2, 2. And then we have this, and on the right-hand side, we get 1, 2, 1. Okay, so then the next step of this gives me 1, 1, 1, and then I get 0, 0, 1, and then I get 0, 1, 1. And then, of course, on the right-hand side of this, I have now 1, 1, 1, 1, 0. Okay, so now here I have a problem. My A22 is equal to 0. So I need to switch row 2 needs to switch with row 3. So when I do that, I end up with 1, 1, 1, 0, 1, 1, 0, 0, 1, which is perfect because I'm ready to back solve. 1, 0, 1. Okay, and then you proceed as before. Okay. So row interchanges do affect everything. We'll talk about that in a minute. And the inversion of A in other words, I want to find A inverse. All right. That's basically A times some matrix X is equal to the identity. All right. With X and n by n unknown matrix. Okay, so X is a vector, a matrix that has x1 vector, x2 vector, all the way up to xn vector. And I is the matrix that has E1 vector, E2 vector, all the way up to En vector. Okay, so this is n systems of equations. So n systems of A xn is equal to En. All right. So you can solve it like that. So therefore, the number of multiplications and divisions of A inverse is 4 over 3n cubed minus n over 3. So that's approximately 4/3 n cubed. Okay. So it's 4 times the operation count of computing A is equal to LU. So it results in 4 times the operation count of A is equal to LU. Okay. So when we have a problem, we can do partial pivoting. And this is a really interesting example. So x1 plus x2 plus x3 is 1. x1 plus 1.0001 x2 plus 2x3 is equal to 2, and x1 plus 2x2 plus 2x3 is equal to 1. So if you can see, this is literally just a modification of the last example, except I've changed it in this middle term, which was just x2 as gone to 1 plus epsilon times x2, where epsilon is 10 to the minus 4. So just by changing this a little tiny bit, let's see what happens. So now we start off with 1, 1, 1, and then 1, 1.0001, 2. Let me move this over, 2, and then 1, 2, 2. I think this first number is supposed to be a 1. Right-hand side, we get 1, 2, 1. Okay, so now we get M2, M21 is 1, and M31 is 1. So we go to the next step, and at the next step, we get 1, 1, 1. We get 0, 0.0001, 1, and 0, 1, 1. On the right-hand side, 1, 1, 0. Okay, so now A22 is not 0, but it's really, really small. Much, much less than 1. And so M32 then becomes A32 at the second phase divided by A22 at the second phase. And that just becomes 10,000. All right, so that's a very dominating number. So we keep going, and we get 1, 1, 1, 0, 0.0001, 1, and then we get 0, 0, and negative 9,999. Then on the right-hand side, we get 1, 1, 1, negative 10,000. Okay. So with 3-digit arithmetic, we get x3 is 1, x2 is equal to 0, and x3 is equal to 0. But the true solution, x is 1.0000 minus 1.0001 and then 1.0001. Okay. All right, so the problem became that the MIK was so big. So here is our problem. So if MIK is much, much bigger than 1, any round off error in AKJ at the K stop will be greatly increased. In the calculation of finding the next AIJ at K plus 1, because that's AIJ at K minus MIK, which is huge, times AKJ at the K thing. So it messes us up completely. All right, so what we'll do is partial pivot. So here's the fix, is to partial pivot. All right, so that is at each step, switch rows so that the largest element appears in the top pivot position. Okay, so obviously this is going to mess up A is equal to LU big time. Okay, so if we do that, we end up with 1, 1, 1, 1. Nope, that's a 0. 0.0001, 1, 0, 1, 1. Right hand side is 1, 0, 0. And so now I'm going to switch row 2 is going to switch with row 3. And then I'm going to get 1, 1, 1, 0, 1, 1, 0, 0.0001, 1, and then the right hand side is 1, 0, 1. And then when you get to the last one, you get 1, 1, 1 at the top. You get 0, 1, 1, and then you get 0, 0, 0.9999. And then my right-hand side is 101. And now I get x3 is 1, x2 turns out to be, this is 1.000. This is minus 1.000, and x1 turns out to be 1.000. Okay, so how do we implement this? So we have an algorithm. Okay, so we have 4k equal to 1 all the way up to n minus 1. We're going to let ck is going to be the max of k equal of all the k less than or equal to I up to n of the absolute value of aik at the kth point at step k. Okay, so we'll find that max. So if I is bigger than k, then switch rows. RK with RI and proceed with step K. And here I is the smallest index for which the max is attained. So you have to keep track of that. Okay. Right. I think we're up to, that was 8. We're up to number 9. Okay, so the effect of row interchange on the LU factorization. Okay, so pivoting changes A is equal to LU. Okay, row interchanges on A okay, can be represented by multiplication of A by a permutation matrix P. So if you switch the rows in P and multiply it by A, you'll switch the rows in A. So you end up with P, A is LU. So L is still the lower triangular matrix that you construct from the multipliers. U is still the upper triangular matrix that you obtain without pivoting. But P multiplies by A has changed it ever so slightly. Okay. So for example, if P is 0, 0, 1, 1, 0, 0, 0, 1, 0. So that's P. Then P interchanges rows 2 and 3 and rows 1 and 3. So P interchanges rows 2 with row 3 and row 1 with row 2. Okay, so AX equals B is solved, can be solved without row interchanges. Then if you do PA, X is equal PB, this can be solved without row interchanges. Okay. So if row interchanges are required, to reduce AX equals B to UX equals G, and here again, A is non-singular, then A cannot be factored as A is equal to LU. Instead, you have PA okay, now P is, remember, P is simply a matrix with the rows switch. So P inverse just switches those rows back. Okay, so A then is P inverse L U. And P inverse simply equals P transpose. So that implies that A is equal to P transpose L times U. But this thing is no longer lower triangular. Okay, U is still fine. U is still upper triangular. Okay. So using A is equal to LU, or A is equal to P transpose L U to solve AX equals B requires less operations than Gaussian elimination. When these two things happen. A is symmetric, or A is tridiagonal. Okay. Variations of Gaussian elimination. Okay. All right. So modifications or simplifications. Ooh, I spelled that wrong. Based on special properties of some class of matrices. For example, symmetric or positive definite. Okay, and there are ways to write Gaussian elimination in a more compact form. Okay. All right. So the first one is going to be the Gauss-Jordan method. Okay, so the Gauss-Jordan method, we want to take this matrix, A11, A12, all the way over to A1N, A21, A22, all the way over to A2N, dot, 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 AN1, AN2, ANN, all right. B1, B2, Bn. So we want to take that and make it look like 1, 1, 1, 1. All zeros here, all zeros here, B1, B2. Yeah, right. B1, 1, B2, 2, Bn, N. Okay, so if we can do that, then we can read off X what each one is. So we want to eliminate entries above the diagonal and go to row echelon form. Now, for me, I'm thinking this is reduced row echelon form. When we move the entries above below the diagonal is row echelon form. But when you remove the ones on top of the diagonal, that should be reduced row echelon form. Because reduced row echelon form takes it all the way down to the identity. So I'm going to slide in here, reduced. Because that's what I think it is. Okay, so at step K, here's algorithm. So step K. All right, you choose the pivot element. And so you have AKJ at the K plus first step is equal to AKJ at the K step. And then I'm going to divide by AKK at the K step. All right, and we do this for J equal K to N. And we know that BK, whoops, BK at K plus 1 is going to equal BK at K divided by AKK at K. All right, so we do that for J is equal to K through N. All right, and then you have A, IJ at K plus 1 is equal to aij at k minus aik at k times akj at k plus 1. Okay, and then bi at k plus 1 turns out to be bi at k minus aik at k times b. I don't know why I want that to be a bk at k plus 1. Okay. So this requires approximately n cubed over 2 multiplications and divisions. And it's 50% more multiplications and divisions than Gaussian elimination. Okay. Can be used to produce a matrix inversion program. That uses a minimum of storage. Okay. All righty. The next method, number 2, is the Koleski method. Okay. So let's just define let A be a symmetric matrix of order n. A is positive definite if. Now, I don't know if you guys remember the definition of positive definite, but I'm going to give it to you. So it's positive definite if X transpose AX, all right, which is equal to the sum I equals 1 to n, the sum, oh, that's ugly. The sum J equals 1 to n of Aij times Xij, Xi, Xj. If that thing is greater than 0 for all X, in Rn, okay? So 1, A has to be not n by n. 2, A has to be non-singular. And 3, A, K, K has to be positive. So all the diagonal entries are positive for 1 less than or equal to K, all the way up to N. So these conditions right here eliminate matrices, certain matrices from consideration. Okay. So I think I have just enough time to look at this matrix. So here's an example. So here's a matrix A. And A is 2, -1, 0, -1, 2, -1, 0, -1, 2. So now I'm going to take the vector X, which is X1, X2, X3. So X transpose AX is to take X1, X2, X3, multiply it by the matrix A, 2, -1, 0, -1, 2, -1, 0, -1, 2, and then multiply that by X1, X2, X3. Okay. So when you multiply all of that out, whoa, too far. This turns out to be the vector X1, X2, X3 times the vector 2x1 minus x2, -x1 plus 2x2 minus x3, and then -x2 plus 2x3. And so then you get X transpose AX turns out to be 2x1 squared minus 2x1 x2 plus 2x2 squared minus 2x2 x3 minus 2x3 squared. And with a little clever algebra, I can write this as x1 squared plus x1 minus x2 squared plus x2 minus x3 squared plus x3 squared. And that is definitely greater than 0. Okay, so that's how you show something is positive definite. All right, so I will give you the Koleski. Well, here's the actual method. We still have 2 minutes. Okay. Asymmetric positive definite matrix can be conveniently factored into A is equal to L transpose. Okay. And we'll pick up here on Thursday. Okay, so as we're nearing the end of the class, I have decided that I am going to count your exam 1 as a homework. Basically, the only exam that we're going to have is the final exam, which will be very much like the homeworks. So I'll give you a final exam and you'll have one more project. Okay, so that's how we're going to end the class. Any questions?
Yeah, I have a couple of questions. I think I should meet you in your office.
Okay.
So.